So can somebody tell me what danger of extrapolation means? Like, what is extrapolating something? Nick, what do you think?
When you use a number outside of the data set, you'll get a wrong answer, like a negative answer.
Perfect. So what would be the lowest number that I could use to predict in this data set? 11. What could be the highest number? 27. I could predict nothing outside of that. So when it asks me to predict, I think in the last example it asked me to predict 20. So I plugged 20 in for X, and that was okay. Then it asked me to plug in 5, and I got a negative answer, which didn't make any sense. Yes?
What if the answer is positive, though? Like, if you put 10 into the X, that will still be a positive.
Even if it were still positive, 10 would be outside of the range, so you still have that danger of extrapolation there, even if you get a positive answer. So the next question asks me, it's kind of going backwards, it's asking the opposite. So it says, suppose we want to know how many days after injection of cancer cells would the average tumor size be 500. So it's asking me to go backwards, essentially, where it's giving me the tumor size, and it wants you to figure out what the number of days would be. So the most sensical thing to do would be, okay, well, let's plug in to y hat, and then solve for x. But I'm going to tell you right now, that is wrong, okay? So never plug into something that has a hat in it, okay? So if it asks you, like it gives you a y, and it wants you to solve for an x, you actually have to switch the x and the y list. Okay, so right now, these are the 11 through 27 is my x, and the 150 through 740 is my y. So I want you in your calculator to go ahead and type these back into your list 1 and list 2. If you still have them, then great. If not, go ahead and put them in your list 1 and list 2. Don't switch anything yet. I'm going to show you how to do that. Yes, and what you were supposed to do for that, and I'm going to go back and talk about it, is switch the x and the y. So if it's asking you, basically it gives you a y, and it's asking you to find the x value. So you cannot plug into something that is a y, that has a hat on it, okay? So essentially, when you do stat calc 8, what is your linear regression equation? Y hat equals, I guess it's up here. Yeah, so negative 269.75 plus 37.25x. So algebraically, you would think, okay, I'm just going to put 500 here and then get x by itself. But anything that has a hat on it is a predicted value or a predicted variable. And that's the variable that we're solving for. So we don't ever plug into something that has a hat on it. I want you to write that down. Don't plug into a variable with a hat. So in order to actually solve for this, we're going to have to switch the L1 and the L2. So what I want you to do is go to stat calc 8, and I now want you to make your X list be L2 and your Y list be L1.
That's all?
And then hit enter. Your new equation will now be an x hat equation. So x hat equals a plus by. Where now you're plugging 500 in for the y and getting a predicted x value. Yes?
It's telling me that there's an error in mismatch.
Means that whenever you typed in the original data set, they probably aren't equal, like you typed in something wrong. Yes? Oh, so here, bring it here and I'll clear the memory. Once you've switched them, now it becomes x hat, and now I can plug in 500. The rules for extrapolation still apply here, but now I'm looking at the y list. So what's my minimum y that I could plug in? 150, and then what's my maximum y that I could plug in? 740. So somewhere between 150 and 740 I could plug in, and 500 works with that. Okay, so what we're going to do next is look at, and you guys will have some of this on your homework, and we talked a little bit about it last class, but just looking at what certain points, adding certain points do to your R value. So if I were to find the mean of the x's and the mean of the y's, that point would exactly be in the very middle of my regression equation. So the average x, the average y, will go in the middle of my regression equation. Will that point always be on the regression line? Do you think? The answer is yes. So the ordered pair x bar, y bar will always be on the LSRL. So I want you to make yourselves a note of that. If I found just the mean of the x's and the mean of the y's, that would always be on my LSRL, and it'll always be the middle point.
I have a question like the last slide. If we plugged in 500 and like got a number that wasn't, or like for the x got a number that wasn't between 11 and 27, would it be
That's still okay.
still okay?
Mhm.
Okay.
So here's my data, just 4 through 8, 2 through 9. We don't have any context for this, but this is just a scatter plot with a positive slope and a strong positive correlation. If I added the data point 5, 8, what happened to my correlation? It got weaker. Did it change my slope too? What happened to my slope?
Got smaller.
Got smaller. If I added the point 12, 12, what happened to my correlation? It got stronger. Why did it get stronger?
It has another point to identify.
It basically is like adding another point onto my already existing LSRL. It's making it stronger because now it's giving me more data to predict. So before I could only predict between 4 and 8. Now I can predict between 4 and what? 12. So it's giving me more to predict. If I add 12, 0, what happened to that? It got weaker. It also became what? Negative. So it became weak and it became negative. So that just kind of threw everything off because it's located on the x-axis. So just know when we're talking about things that are resistant and things that are not resistant, the LSRL and the correlation coefficient, which is the symbol what? What's correlation coefficient? R. So R and the LSRL are both measures that are affected by extreme values. So they are not resistant. This is called computer output. So sometimes when you're given bivariate data, you'll be given a list with two sets of data, and you'll put them in your calculator and you will find the stat calculation linear regression. So the first way is by getting 2 lists of data. That's like the raw data. The second way that you could be given data is called computer output, which is what this is, computer output. So this would be an example of 2 lists. this would be considered computer output, where we don't have the raw data, we just have what the computer has given us. So we can't extract the raw data from this. And we're only going to use part of it this semester, and then next semester we're actually going to learn how to read all of it. So whenever you see something like this, the only numbers that you need are these two. We're going to cross out everything to the right. And then these two, we're going to cross out this r squared adjusted. So in order to read this, it's giving you, like the first two numbers that you see are giving you the slope and the y-intercept. So whatever number is next to the word constant is going to be considered your y-intercept. And usually it comes first. Usually it's your top one, but you'll see on your homework it's actually the second one. So sometimes the order reverses and it gives you the slope first and the y-intercept. So just know that it's always next to the word constant. Then the one that's next to, in this case, it's days, but it's always your x variable. Whatever the context is of your x variable. The number next to it is going to be your slope. So I'm going to create an LSRL from those two numbers where it would be y hat equals negative 269.75 plus 37.25x. Your constant is your y-intercept, and then your x variable is your slope, where y represents tumor volume, and then x represents days after injection. So if I did not have the original data, I would just have to read this computer output. Below, you will see this S. That represents the standard deviation. You can't really see that purple very well. Standard deviation of the errors or of the residual, which we'll learn what that is in a minute. And then your r squared is your coefficient of determination, which is actually your r squared, like your correlation coefficient squared. And we'll learn what that means in a second, but if I were reading this graph or this computer output and I wanted to figure out what r was from that, I would have to take the square root of r squared. So I'd have to do that by hand. And then your sign will always match the slope. So can somebody take the square root of 0.997 for me?
What do you mean by the sign matches the slope?
So r can be either positive or negative, right?
Mm-hmm.
And so if I take the square root of a positive number, I'm always going to get a positive number, no matter what. So I would make it a negative r if my slope was negative. And it would stay positive if it were positive. So what is the square root of 0.997? 0.998. And it's going to stay positive because the slope is positive. If the slope were negative, I'd make it a negative 0.998. So we're going to go through an example together. If you turn to page 106, I think, yeah, go to page 106. So this example is talking about hand span. So hand span is the distance from the tip of a person's little finger to the tip of their thumb when the hand is spread out. Researchers gathered data in order to predict a person's left hand using their right hand. So maybe they're not exactly the same. The scatter plot of the data has a linear form, and then this is the computer output in inches. So let's go ahead and circle the things that we need. These two numbers, these two, and then we're going to cross everything else
So we don't
out.
really have to care about them right now, or we will never have to care about them.
Not yet, not till the very end of second semester. So for now, we do not need them at all. So which one, if I'm going to make the LSRL y hat equals, which one would be my y-intercept? 1.4365. Another thing to mention is computer output typically goes out more decimals than you would on your calculator. You need to use all the decimals whenever you're writing a LSRL from computer output. So if it went out 8 decimal places on your computer output, do not round it. Use all 8 from what it gives you. So it would be 1.4365 plus what? 0.9383x. And then I'm going to make sure to define my parameters. So my x and my y. What's my x? Hand span, right hand span in inches. And what is my y? Or I guess you could say y hat. What would my y hat be?
Left-hand span,
So the right span, that's always my x variable.
relationship between.
So it gives me my x variable right there. And in the context of the problem, it says that they use their right hand span. That's the data that they collect to predict the left hand span. So basically, I'm given the right hand, I'm predicting, so predicted left hand span.
You have to like predict it every time.
If you put a hat next to it, I usually do the y hat with predicted. Number 2, it says, what is the correlation coefficient? So what symbol am I looking for? R. So I need to do what to find R? 0.902. Because it's in a percentage.
Is it always in
Oh, there it is.
or R?
Mhm. Mhm. So what is the square root of 0.902? 0.94997. Okay, try to interpret that with your table.
Linear?
Yes. Remember LSD, linear strength direction.
You have to say like between right hand span and left hand.
Yeah, so you need to give the context of the x and the y variable.
Which is the like
Okay, the next one says, what is the coefficient of determination? So that is the r squared, which is what they gave me in the problem. So I'm going to say r squared is 0.902, or you could say 90.2%, but I like to keep things consistent and just keep everything in a decimal. If you flip back to page 99, you'll see the coefficient of determination. The definition of that is it gives the proportion of variation in y that can be attributed to an approximate linear relationship between x and y, which all of that doesn't really make a lot of sense. So I'm going to try and explain it to you to the best of my ability, but you do need to memorize the script in that. So this number right here is about 90%, and so that number represents, so 90% of the reason why your left hand span is because of your right hand span. So 90% is attributed to what your right hand span is, predicting your left hand. The other 10% could be due to other things that have nothing to do with your x variable. So let me give you another example that might make a little bit more sense, because this right-hand span, left-hand span is not necessarily a good one. So let's say that I was collecting data and I was collecting how well you did on a test by measuring the amount of sleep. So your x is amount of sleep, your y is your test grade. And I got a strong positive linear association between the two. And let's say that my r squared was 0.753. And I'm completely making this up, but let's say that it was 0.753. That would mean that 75% of the reason why you made that grade was because of the sleep. The other 25% could be because of why. What are some other things that help you get a good grade? Studying. What else? Paying attention in class. Your natural brain ability. I mean, things like that. Just other things that pertain to the grade that you made. Consider those like the extraneous variables, but the only one that we are measuring is amount of sleep. So, in the context of r squared, or in the context of this problem, 90% of the reason why your left hand span is the way it is because of your right. The other 10% is because of something else. If you try to explain that in your own words the way that I did, you're going to get it wrong. Because trying to explain that in your own words doesn't work. Explaining it in the way that the script gives it to you will work 100% of the time. The r squared is 100% for that. So look at the script on page 99, and I am going to write approximately what is my r squared in a percentage, 90.2% of the variation in what is my y variable in the left hand span can be explained by the LSRL of right hand span and left hand span. So like I said, my interpretation was practical, but this is something that you do need to get word for word because they are very picky about it. Okay, I want you to try 4 through 6 with your table. We've done all the stuff that you don't know how to do, but you can do the rest. So I'm going to give you 4 minutes, and then we're going to check it. So yours does not have to be exactly like mine. However, it needs to be saying the same thing. And what you may think is saying the same thing may not be what the AP graders say is the same thing. So that is why I have created these scripts that are foolproof and they work 100% of the time. So for number 4, basically what it's saying is for every inch that your right hand span increases, your left hand span increases by 0.9383. So they're not directly proportional. Very interesting. For the y-intercept, it wants you to interpret it even though it doesn't make sense. So always go through with the interpretation, but then explain why it doesn't make sense. So the interpretation would be when your right hand span is 0 inches, your left hand span is 1.4365 inches. But why does that not make sense?
What if you don't have a right hand?
Because you can't have a right hand.
But then would your left hand be 1.4 inches?
I have both my hands. I don't know.
We're not here to talk about the exceptions. Can't have a 0 inch right hand span. Then number 6, it wants you to predict What is something that we don't know from computer output when we're predicting? We don't know.
The range or the domain.
Well, we don't know the domain, so we don't know if we're extrapolating or not. So we just assume and hope that we're not.
Really? Oh, great.
So with this, you just predict.
Because this doesn't make sense, doesn't that mean we can detect when it becomes extrapolating?
If you got a negative answer, then yes, it wouldn't make sense. But
It can still be an extrapolation.
So you don't know which the low.
you wouldn't want to plug in like a negative number, and you wouldn't want a negative answer. But
Wait, so if you got a negative answer, what would you write? Would you
just say danger of extrapolation. But they won't ever have you extrapolate with the computer output.
So, but say they gave us 2 data sets, would we still put the number and say this number is, or just write the data set?
You would solve it, and then you would say that it's danger of
So
extrapolation.
you can't like skip this one.
No. So a residual, and this is something that you saw in your homework yesterday, but we did not get to. A residual is the vertical distance that a point on the scatter plot is from the LSRL. So not every point directly hits the LSRL. That LSRL tries to minimize that distance, but you're still not always going to be perfect. Every point's not going to be perfectly on it. And so a residual just measures that distance from it. It could be a positive distance if you're above, or if you had a negative residual, that would mean that it would be below. So the sum of the residuals is always equal to 0. So if I added up all of the residuals, that would equal to 0. So what I'm going to do is we are going to put our data points. We're going to try to discover how to create these residual plots. So in your list 1, I want you to put your x's. And in your list 2, I want you to put your y's. Then I want you to fill out this y hat. So find the LSRL and the R. And then I also want you to plot your scatter plot. So 3 things. Did everybody get that? So your y-intercept is negative 0.0604 plus 1.0577x. And my correlation coefficient is 0.9288. If I were to estimate what this line would be, I would say it probably looks something like this, but I'm not as accurate. Has about a 1 slope and a negative 0.06 y-intercept. Yes?
Did you say that like we have to graph it like exactly? Or is that like only?
No, even like if you didn't have any numbers, if you just drew the picture, that would be fine.
Just like lines on the calculator numbers should be changed.
For this activity, yes, but whenever you're drawing it on for your response, no. Okay, so the next thing it wants us to do is to calculate the fitted value. So basically, all of my predicted into my list 3. But since we know that our list can act like an Excel spreadsheet similar to it, and that we can actually plug in a formula, how could I get all of these to produce my predicted y? How could I figure that out? Yeah, so I could type in the LSRL into the top. So does everyone remember how to do that? So I'm going to go to my list 3 where it's highlighted. So I need to hit up and then hit the enter button. Now you see it blinking. Now I'm going to type in my LSRL, which is negative. Oh, my negative button is down here. Negative point, what is it? 0.04 plus 1.05? 0577. And then what is going to go, instead of putting X, what am I going to put? L1, because those are my X's. So second one, close parenthesis, enter. So these are the numbers that you should get. That's my list 3. For my list 4, this will actually be my residual list. The formula for residual is actual minus predicted. You can write that somewhere. Actual minus predicted. The way I remember that is we are in AP statistics. AP. And I guess with using the variables, it's y minus y hat. But it's your actual y value minus your predicted. So in my list 4, what would my formula, like what 2 lists am I going to put in for my list 4? What would that look like? L2 minus L3. L2 minus L3. So go ahead and get those. These are the numbers that you should have gotten. What do you notice about the numbers?
They equal 0 if you add them all up.
If you add them all up, they equal 0. Some are positive, some are negative, which means if they are negative, that they are above or below. So 3 of them are below the LSRL, and then 4 of them are above the LSRL. If you added them all up, they would add to 0. I'm going to tell you that there are very rare cases where you have to go through all of these steps. Typically, the AP test will only want you to find like one individual residual, which means you could just do it by hand for 1 point, or they want you to make a residual graph. Yes?
Is that why when you draw your line, 3 of your points are below?
Yeah, so when I drew the line, 3 of them were below and then 4 of them were above.
Why are the green and red? What does that mean?
The green were the negative ones, meaning they're below the LSRL.
Oh, that's not.
And then,
I mean, that's just separating the positive.
yeah, like positive and negative. Okay, so the next thing that I want to do is create a residual plot, because that's where on your homework they asked you, is the linear model appropriate? Basically, would an LSRL be the right thing to do when finding the relationship or not? And so we don't know the answer to that just based on our correlation coefficient. We actually have to plot a residual plot. So I'm going to show you in the calculator how to do so. So from here, you have to calculate the LSRL on X and Y, and what the calculator does is it actually stores your residuals. That's probably what the stat wizards are doing, is it's storing your residuals inside the calculator, and it will directly graph them for you. So I'm going to go to second y equals, and I'm going to change my plot to be a scatter plot. Yours is probably already on there.
Okay.
My X list is going to be the original X list, so L1. So your X list should be whatever your X's are in your stat edit, which is my list 1. Then the Y list is going to be, if you hit second stat, you'll see -7, yours could be 8, but you'll see resid. Now this will only show up if you have already done stat calc 8. If you haven't, then the calculator has no residuals.
How did you change that one again?
Second stat, and then mine was option 7, but yours could be option 8. From here, I'm going to hit zoom 9, and here is my residual plot. So if I were to draw this on a test or something, my y-axis represents residuals. My x-axis represents whatever my x is in context, and there is no context in this example.
So what does X mean then?
X is whatever it is. So in the last example, it was like your right hand span or whatever. So you'll just label it whatever your x-axis is. And you'll notice how 4 are above and 3 are below, because 4 are positive, 3 are negative. And when you add them all up, they should add to 0. So this x-axis is a long 0. Basically the distance, if you're on that point, then you have no residual. You're exactly on the LSRL. And then some are above, some are below. Whenever you're deciding whether a residual plot is a linear model is appropriate or not, you want this residual to be completely scattered. You want it to have no pattern. So no pattern is good. We want it to look like a bunch of stars in the sky. If it has a pattern, then that means that the linear model is not appropriate. So I want you to go back to page 99 really quickly, where it says, is linear model appropriate? The exact script would say, since the residual plot, in this case, displays no pattern, a linear model is appropriate for describing the relationship between x and y.
Wait, but why would you said if it was near 0, that means that it would be on the LSRL, then why wouldn't we use a linear plot if it was on the LSRL?
Do what?
You said when it's closer to 0, it's on the LSRL.
Yeah, so if I had a dot that was like right here, then that would
If
mean,
it doesn't have a pattern, it's
right.
So why, if all of them were on that, why would it not be okay to use a linear?
It would be okay. If they were all really close, that would actually be even better. Because that would mean that our LSRL is really good at predicting our y values because they're all so close.
Wait, so
Do you mean there shouldn't be a
so
linear
this is not good enough?
No, so I think what you're asking is if I had, so for instance, if my residual plot, I'm just going to erase these. If my residual plot looked like a linear pattern like this, that would not be appropriate. Because it means that a linear model isn't the right thing to use. I would need to go on to something else, like maybe an exponential model, quadratic, or something like that. So we want our residuals to be very scattered. We don't want them to be any sort of pattern. If it had a pattern like this, that wouldn't be good either. So most residual plots will not contain a pattern. So I don't want you, like ours looked something like that. I don't want you to try and create a pattern from that. This is like one of our biggest downfalls as a class is you're over analytical, like minds are like, oh, but I could create this pattern. No, it's probably, unless it is so obvious, it's not going to have a pattern, okay? Yes. So the one that I drew, like the line, like that, that would be a pattern. Something like that would be a pattern. Like it is going to be so obvious, but if you had something like that, that is scattered, okay? Look at it. That is scattered. That is not a pattern. No, it's not a pattern. It's not a pattern. If it were like this,
So is it like
that is a
the
pattern.
more points there are, will it be more obvious?
Yeah, I think so. Okay, so I want you to go to number 8. We're going to skip down to number 8. Perfect. So since,
You can't say that it's describing it, you can say no context.
right. So since the residual plot displays no pattern,
Does it have to be exactly word for word in the script, or if it does this?
if it means the same thing, then it's okay, but I want you to try and stick to the script as much as possible because
Like I said, shows.
that's fine.
Okay. Just making sure.
A linear model is appropriate for what? What is it appropriate for?
For describing.
For describing the relationship
Can you just say between X and Y?
between X and Y, but otherwise it'll normally have some sort of context.
You have to like write is appropriate for describing.
Yes.
Appropriate.
Nope, you need to write it all. Okay, so I want you see this second graph on number 6. So normally when you're making your residual plot, we will, like 99.9999% of the time. Guys, why are you talking? Stop. We will use X, which is our L1, and then our residuals will be the y list. So x list is x, y list is residuals. We are going to make a second residual plot where the x list is our predicted y's and our y list is residuals, just to show you what they look like and if they are the same. The only reason why we do this is just to show you that they end up looking the same. So how would I do, like, what would I make my x list in my calculator? What did we save that as? Brianna noticed this, that it looked the same, but the numbers were different.
Yeah, but just
And that doesn't matter because in a scatter plot, numbers don't matter. It's just what the dots look like and the relationship between the points. So no matter if you did y hat versus resid or x versus resid, they're going to be the same. The only reason that we show you this is because sometimes a multiple choice question on the AP test will ask you about this. For your purposes, the only one that I want you to make for like a free response question or something like that would be x versus resid. Because you don't have to go through making a list 3 and a list 4 ever again. You really only need to find the LSRL and then graph your residuals, because that's what it'll mostly be asking you to do. Yes?
On like a free response, it'll be exactly like question 5, where it says create a residual plot.
Yeah, so it'll say, and it won't even tell you to create a residual plot. It'll just say, is the linear model appropriate? And from there, you have to know, okay, I need to make a residual plot. That's my proof. And then I need to comment on it. So it's not going to say create a residual plot because it's not that nice. It's just going to make sure, it's just going to ask you if the linear model is appropriate or not. And you have to make a residual plot for that.
You still have to draw it, or could you just do it on your calculator?
Draw it. Whenever you had the data originally, it looked like everything was kind of grouped together. And then you had this 45,205 that seemed like it was kind of out in its own space, right? So whenever you removed that, you noticed that the slope changed. It drastically changed. It went down because whereas one would probably be something like that, now it's directly going through the points and they're all closer together. So the definition of an influential point is that it changes the LSRL. It has nothing to do with strengthening or weakening, because if you noticed from 9 to 11, it actually weakened. In fact, the R went from 0.76 to 0.58, which you're probably thinking, why did that happen? And I guess the only reasoning for that is that it just gave you 5 more data points to predict or give you without danger of extrapolation. So it just stretched it out further. And I can't really tell you the reason why it weakened, but it did weaken. But it doesn't matter because the influential point means the slope changes. So you could have a good influential point or a bad influential point. It could strengthen or it could weaken. It doesn't really matter. It just changes the slope. So that is the definition of an influential point. If you notice right above that, it says outlier. An outlier is the data point with the largest residual. So that will always strengthen. If you take that out, that will always strengthen your R value. Yes?
Is R squared kind of like a reliability of the graph kind of thing?
Mm-hmm. So outlier means that it is always going to strengthen it if you've taken it out. So an outlier is always bad. An influential point could be good or bad. So the difference between the two, outlier is the one with the largest residual. And then an influential point means if it's taken away, it would affect the slope. So it doesn't matter if it strengthens or weakens it. For the interpretations, if you want to check them, I'm just going to say them out loud. For the slope, you should have said for each unit increase in age, and we didn't know if it was like days or weeks or months or years. I would probably assume it's days, but for each 1 unit increase in age, there is an approximate increase of 0.6865 units in range of motion. For the R, you should have said there is a moderate positive linear relationship between age and range of motion. And for R squared, you should have said approximately 34.5% of the variability in range of motion can be explained by the LSRL between age and range of motion. And then the last one is that none are resistant. They're all affected by extreme values.
What was for R squared?
Approximately 34.5% of the variation in range of motion can be explained by the LSRL between age and range of motion.